Welcome back to this next video in which we are discussing headaches. Okay, so in this next video we're going to discuss the mechanism by which use-dependent voltage-gated sodium channel blockers actually work. And remember what I've told you about what these things are capable of doing. It is quite incredible. They are capable of silencing neurons from firing action potentials at all if those neurons are trying to fire action potentials too rapidly. So if a neuron is being stimulated to fire action potentials that would be too frequently, that neuron will be silenced completely in the presence of a use-dependent voltage-gated sodium channel blocker and will not be able to fire any action potentials at all. Whereas other neurons that are firing action potentials at a perfectly reasonable rate, they are not going to have any of their action potentials blocked by the use-dependent voltage-gated sodium channel blocker. So it just will block neurons that are trying to fire action potentials too frequently. And remember, this is the basis for why the use-dependent voltage-gated sodium channel blockers are so effective at preventing epileptic seizures and why most of them are used as anti-epileptic drugs. However, we've got these two examples here, topiramate and also sodium valproate, that are also used for the prophylactic treatment of migraine headaches. And we can kind of understand how they might actually manage to prevent cortical spreading depression because, of course, at the rim, the expanding rim of the cortical spreading depression is overactivity. The neurons at the front, they're firing at a far too fast rate, and these use-dependent voltage-gated sodium channel blockers, they will block that overactivity, and potentially if you don't have the overactivity, then maybe you don't get the following underactivity, maybe you don't get the following depression, and if you don't get that following depression, maybe you don't get the same changes in extracellular fluid chemicals that you get in the full cortical spreading depression, and therefore whatever the mediator is that goes to the meningeal nociceptors and activates them, maybe that's not going to go up anymore, and therefore you won't get the activation of the meningeal nociceptors, so you won't overall get the migraine headache. So we can kind of potentially see a way that use-dependent voltage-gated sodium channel blockers could be effective at blocking cortical spreading depression. So what I now want to do is look into the mechanism in detail. I want to explain to you how these drugs successfully block neurons that are trying to fire action potentials too frequently completely, whilst not affecting neurons that are firing action potentials at a perfectly normal, respectable rate. And this is a complicated mechanism, but it's a mechanism that is well worth understanding because it's the mechanism by which most of the anti-epileptic drugs actually work. And we will see other examples of the use of use-dependent voltage-gated sodium channel blockers and indeed use-dependent voltage-gated calcium channel blockers later on in this video. So it's an important mechanism, so I'm going to take the time to actually explain it to you properly. So, for this explanation, however, we need to have at the forefront of our mind an understanding of the action potential. We also need to have an understanding of the different states that voltage-gated sodium channels can be in order to understand this. So, I'm going to do that background first, and I don't mean to patronize my viewers. We do need to have a very clear understanding of the action potential for this mechanism to actually make sense. So, let's begin by going over the background of the action potential. Okay, so to discuss the action potential then, I'm going to draw a picture of a neuron, and this is going to be a classical neuron, a multipolar neuron. So we will have dendrites here, so here is one dendrite, here's another dendrite, and then we'll have the axon here. And I've got a nice thick axon there, and I won't bother drawing the bottom of this. What that we've got will do as far as our picture. I've got a few dendrites shown here. Here's the cell body, and here is the axon. Now, remember, the dendrites are going to be collecting stimulatory and excitatory signals for the neuron to fire an action potential, but the action potential doesn't actually begin in the dendrites. It begins at this junction between the axon and the cell body, and that junction has a special name. That is known as the axon hillock. So the axon hillock is the junction between the cell body of the neuron and the axon, this junction here, and that's the first place where the action potential is actually going to begin. So What is an action potential? An action potential is a propagating disturbance in the electrical potential difference across the cell membrane. Now, normally, the electrical potential difference across the cell membrane of the neuron is kept at resting electrical potential difference, and it is around negative 70 millivolts. So we call this VM for membrane voltage, and it's usually at negative 70 millivolts. And remember what this actually means. This means that the electrical potential in the intracellular fluid is 70 millivolts lower than the electrical potential in the extracellular fluid. So if you were a little man in the extracellular fluid and you moved into the intracellular fluid, the electrical potential of that area would have gone down by negative 70 millivolts. So if you were a little man standing here with a machine for measuring electrical potential, and then you moved into the intracellular fluid, the number on your screen of your machine would go down by 70 millivolts. There is an electrical potential difference across the cell membrane of negative 70 millivolts, and electrical potential difference is also called a voltage. So that's what that means, that the electrical potential of the extracellular fluid and intracellular fluid is not the same, and it's lower in the intracellular fluid normally. Okay, now the action potential is going to be a propagating disturbance in this, a depolarization of this. This electrical potential difference across the cell membrane is going to reverse temporarily, so that it actually becomes positive. It goes up to plus 30 temporarily in across a portion of the membrane, and that propagates forward across the membrane. So that's what the action potential actually is. Now, in order for a membrane to undergo an action potential, this disturbance in the electrical potential difference across the cell membrane, it needs to have voltage-gated sodium channels and voltage-gated potassium channels in its cell membrane in a sufficient density. And that's the reason the dendrites can't actually fire action potentials, because they don't have the sufficient number of voltage-gated sodium channels and voltage-gated potassium channels in their cell membrane, whereas the axon has loads of voltage-gated sodium channels and loads of voltage-gated potassium channels in its cell membrane. So let's put them in here. So I drew more complicated pictures of the voltage-gated ion channels for sodium and calcium earlier. We're now going to go back to extremely simple pictures temporarily. So this is representing a voltage-gated sodium channel here in blue, and I've drawn it in the open state, as though it's open, but it's not going to originally be open. It will be in a closed state, and we'll talk about the different states in just a moment. Okay, so here then is a voltage-gated potassium channel. I've just drawn it with the channel open so that it's clear that there is a channel there. So here is a voltage-gated potassium channel, and again I've abbreviated that down to VGKC. K is for potassium, the potassium periodic table symbol. So we've got our voltage-gated sodium channels and our voltage-gated potassium channels, and now we are set up to undergo an action potential. What actually triggers this axon hillock to generate an action potential? It's stimuli coming in from the dendrites. So when another neuron, let's say there is a axon terminal synapsing onto this dendrite here, so there's an axon terminal of another neuron. When this one fires an action potential, it will release neurotransmitter that will bind to receptors, and whether the neurotransmitter is inhibitory or excitatory obviously is important at this point. If it's excitatory, then it will bind to receptors that will then cause depolarization of the electrical potential difference across the cell membrane by allowing positively charged ions of various different types, so potentially sodium or potentially calcium ions, to come into the inside of the cell. If it was inhibitory, it would allow negatively charged ions to come into the cell or allow positively charged ions to leave the cell. So it could allow chloride anions into the cell, or it could allow potassium ions out of the cell if it was inhibitory. But we're interested in excitatory, obviously, because we want an action potential to be generated. So excitatory stimuli on the dendrites will cause positively charged ions to be allowed to come into the cytoplasm of the cell. And when you bring positively charged ions into the cytoplasm of the cell, that's going to change the electrical potential in the cytoplasm of the cell. Positive charge raises the electrical potential of an area. So when you move it from the extracellular fluid to the intracellular fluid, as indeed my arrow is doing here, we're moving positive charge from the extracellular fluid into the intracellular fluid. We raise the electrical potential in the intracellular fluid, and we lower the electrical potential in the extracellular fluid. Now remember, we can draw a little sort of diagram here. These two lines are useful. This was the electrical potential extracellularly. So I will call this, what should I call it? Capital E for electrical potential, and then subscripted capital E for extracellular. This was the electrical potential intracellularly. Now, previously, you had to jump down negative 70 millivolts when you went into the intracellular fluid. So on this vertical axis, then, this is electrical potential. So I'll just abbreviate that down to EP. Okay, so previously there was an electrical potential difference of negative 70 millivolts, and I'll just put that on here. So this was negative 70. You stepped down by 70 millivolts in this step here. Now, if we're bringing positive charge in, we are raising the electrical potential intracellularly up, so this goes up. We will be lowering the electrical potential extracellularly down because we're taking positive charge away from the extracellular fluid, so that will be reducing the electrical potential of the extracellular fluid. So you can imagine that these two lines are going to become closer to one another. The electrical potential difference across the cell membrane will become less negative, and we call that depolarization. Okay, so you let in positive charge, and this is going to be depolarizing the electrical potential difference across the cell membrane all over the dendrites. And you might have more axon terminals synapsing onto the other dendrites that are also stimulating positive charge entry into the dendrites. Now, some of this positive charge is going to diffuse, not all of it of course, but some of it will diffuse into the axon hillock over here. And therefore, what's this going to result in? It's going to result in the increase in the electrical potential intracellularly in this axon hillock region. So now the electrical potential over here is now going to be becoming raised. And again, you can imagine on this graph, this is going to go up. So again, now in the axon hillock region, this is going to result in depolarization of the electrical potential difference across the cell membrane at the axon hillock. So all of the dendrites, they are collecting stimulatory signals which correspond to the letting in of positive charge into the cytoplasm of the cell. This positive charge will come to the axon hillock region, and if it's great enough, it will depolarize the electrical potential difference across the cell membrane of the axon hillock up to the threshold potential for the firing of an action potential. And the threshold potential is usually around negative 55 millivolts. So this is a very important concept, the concept of threshold potential. So normally, in most neurons, the threshold potential is around negative 55 millivolts. So the axon hillock here will generate an action potential if the electrical potential difference across its cell membrane gets up to, or beyond, of course, negative 55 millivolts. So you have to get lots of positive charge coming to the axon hillock to actually do that. And of course, inhibitory synapses, if they become active, they'll be letting negative charge in or they'll be letting positive charge out, and that will be countering this effect. That will be reducing the electrical potential intracellularly in the axon hillock cytoplasm here, and therefore countering the stimulation from the excitatory one. So it's always a weighing up. There's always weighing up going here. We're all going on here. We're always the axon hillock is always seeing if the stimulation overall outweighs the inhibition, and if it does, that corresponds to the electrical potential difference across the cell membrane of the axon hillock getting up to negative 55 millivolts, the threshold potential, and then you will fire an action potential. And what happens when the electrical potential difference across the cell membrane gets up to negative 55 millivolts to generate the action potential? It's that the voltage-gated sodium channels and the voltage-gated potassium channels are going to open. So at this point of the story, I need to tell you about the different states that voltage-gated ion channels can be in. So let me do this here. So on my picture above, it's been very simple because we've just drawn one state, the open state, but initially they're not going to be in that state, they're going to be in a closed state. So let me draw another picture below here. So in yellow now, this is not representing an axon, this is representing the phospholipid bilayer, so the outer leaflet and the inner leaflet of the phospholipid bilayer. And in this picture of the phospholipid bilayer, I want to show you the 3 different states of a voltage-gated ion channel, and we're specifically interested in the voltage-gated sodium channels. However, it's the same for the voltage-gated potassium channels. So here's the first state here, and I just want to actually put something else onto this picture that I won't explain at the moment, but I'll explain later. You'll see in just a moment what that is. So here's the first state, and this is the state that these voltage-gated sodium channels, and indeed, if I'd drawn this in green, it would be a voltage-gated potassium channel, so all that I'm saying applies for both of them. This is the state they're going to be in initially when the electrical potential difference across the cell membrane of the axon is at the moment negative 70 millivolts. And these channels, these proteins, they change their shape according to what the electrical potential difference across the cell membrane is doing. That's very important to understand. This is the closed resting state. So don't just call it the closed state, call it the closed resting state. Everyone will know what you mean if you say closed resting state, because there is another closed state, which is the closed inactivated state. So at negative 70 millivolts, these voltage-gated ion channels, they are stably in this closed resting state, and they will just stay like that forever if you maintain the voltage across the cell membrane at negative 70 millivolts. It's only if you raise it up to or beyond the threshold potential. So this is the state that they want to be in if you are at less than negative 55 millivolts. So at negative 70, of course, you are less than negative 55, you're lower than the threshold potential, therefore they want to stay in this state. And indeed, all of them will be sitting nicely in this state in the axon cell membrane. Okay, and in that state they are not allowing ions to go through them. No sodium ions can come through this voltage-gated sodium channel, and if we were talking about a voltage-gated potassium channel, no potassium ions could go through that. Okay, now, when we depolarize the electrical potential difference across the cell membrane to above negative 55 millivolts, what happens is it really wants to move into the closed inactivated state. And you're probably surprised at what I've just said. You're probably waiting for me to say it's going to move into the open state, but actually the open state is only a transient intermediate. At above negative 55 millivolts, the stable state for a voltage-gated ion channel to be in is not the open state. It is the closed inactivated state. But when it moves to get into the closed inactivated state, when it undergoes the conformational change, a transient intermediate state that is formed is the open state. So I want that drilled into you. The open state is not a stable state. It is a transient intermediate state. It's a transition state from going from the closed resting state to going to the closed inactivated state. So let me now draw this on here. So transiently, when you go to greater than negative 55 millivolts, and I'll put greater than or equal to, although I don't know what the actual state is if you get precisely on negative 55 millivolts, but I think you get the overall message here. Okay, so this is a transient state, and I'm going to put transient here so that that's absolutely clear. So transient state, it's going to go into the open state, and drawing that very simply, I'll draw it like this. So the ion channel opens, and this bit that's dangling on the bottom, that still remains there. So transiently, when you move the electrical potential difference across the cell membrane to greater than or equal to negative 55 millivolts, the channel is going to change conformation, and for a little bit of time, it will be in this state, this open state. So this is obviously called the open state, as you probably realized. Now, let me just extend my cell membrane along a little bit so that we've got space for the final state. So that is not a stable state at all. It's a transient intermediate. It's an intermediate state to move into the final stable state, which is the stable state for the ion channel to be in when the electrical potential difference across the cell membrane is greater than or equal to negative 55 millivolts. And this state is the closed inactivated state. And what happens is this portion here that I've got dangling down, it flips up inside and blocks the pore of the ion channel. And do excuse me whilst I just get rid of that annoying blob. Okay. So let me draw now the closed inactivated state, and let me try and keep them all in view. So closed inactivated state here. So it's a different thing that has happened to close the ion channel. Initially, you can see that in the closed resting state, the entire ion channel is actually closed, whereas now in the final state, the closed inactivated state, the reason that no ions are flowing is different. There is a bit that's on the cytoplasmic aspect here called the inactivation gate. So now I can finally tell you the name for that bit that dangles down there. That's called the inactivation gate. that has flipped back up into the ion channel and is blocking the ion channel on the cytoplasmic aspect there. Okay, so it's now moved into then this final state here, which is the closed, and we call it the closed inactivated state. So there are these three states: closed resting, open, which is a transient intermediate state, and then the closed inactivated state. So really, I would urge you to think about it, however, that there is only really two major states. There is the closed resting state, which is one major state, and there is a closed inactivated state. If the electrical potential difference across the cell membrane is less than negative 55 millivolts, then the ion channels want to sit forever and ever and ever in this closed resting state. If the electrical potential difference across the cell membrane is is above or equal to negative 55 millivolts, then they want to sit forever and ever and ever in this closed inactivated state. It's only when you move between the two states at the threshold potential, when you're moving the electrical potential difference across the cell membrane and it goes through that threshold potential level, that transiently it goes into the open state, and this is an intermediate between these two states. So do just think of this as an intermediate state, not as a stable state at all. Now, a little bit of terminology then. When the closed resting state moves into the open state, so this arrow down here, that is called activation. So we say that the voltage-gated ion channel has been activated and is now in the open state. It's only going to be in that state transiently, though, if the electrical potential difference across the cell membrane remains above the threshold potential. It will then move further. This is a transient intermediate, and now it will change conformations again. The inactivation gate will swing upwards and it will shut the thing, and it will then go into the closed inactivated state. That process, where it moves from being in the open state to being in the closed inactivated state, that is of course called inactivation. Now, that's what happens if you move the electrical potential difference across the cell membrane up. So if it was from negative 70 millivolts and we've moved it up to above negative 55 millivolts, those are obviously the processes that are going to occur. They open for a while and then they inactivate. However, what about the other way round? What if you're coming down? So what if you're at an electrical potential difference across the cell membrane greater than or equal to negative 55 millivolts, and you're now bringing it back down below threshold potential? Maybe you're bringing it back down to negative 70 millivolts. Well, the exact reverse process happens. What happens is now it wants to move from being in the closed inactivated state to being in the closed resting state, and again, it goes through the intermediate step of being in the open state. Okay? So, it's going to go into the open state again, and that process, the reversal of inactivation, what do you think that's called? That is called de-inactivation. So that green line that we've got there, that process is de-inactivation. So when you've moved the electrical potential difference across the cell membrane back below threshold potential, de-inactivation will occur. Now, moving across from this state to this state, or from this state to this state, moving across these arrows is slow. It takes a little bit of time. So once you've moved the electrical potential difference across the cell membrane to below negative 55 millivolts, this will take a little bit of time to occur, especially in voltage-gated sodium channels. Whereas the other bit now, where the open state now moves back to being in the closed resting state, because again, when you're going in the reverse direction, moving the electrical potential difference across the cell membrane back down, the open state is only a transient intermediate. This process will occur very, very quickly in voltage-gated sodium channels, just as activation occurs extremely quickly. So getting across this is much quicker than getting across this. So when you transiently go into the open state again, you will move out of the open state extremely quickly if you are below, if you're going down, basically, is my message. Because you might find this surprising, that actually when you're below, going back down to below the threshold potential, that for a while the ion channels are going to open, but they're going to be open so transiently in the case of voltage-gated sodium channels, because you jump across this bridge very, very quickly. Final piece of terminology, that final green arrow where you're going from being in the open state to being in the closed resting state, that is called deactivation. So we've got a lot of terminology there. Activation, inactivation, deinactivation, and deactivation. Do not confuse deactivation with inactivation. Inactivation is going from the open state to the closed inactivated state. Deactivation is going from the open state to the closed resting state. Okay, so those are the different states that our voltage-gated sodium channels and indeed our voltage-gated potassium channels can be in. And this is extremely important to understand when we're going to be talking about the use-dependent voltage-gated sodium channel inhibitors. Okay, so armed with this knowledge, let's now understand what's going to happen in the action potential. So when we bring the electrical potential difference across the cell membrane of the axon hillock up to beyond the threshold potential, the voltage-gated sodium channels and the voltage-gated potassium channels in this little portion of the membrane at the axon hillock are going to now open, and both of them will be activated to open. This arrow here is going to happen for both of them. They both activate to open at beyond negative 55 millivolts, so greater than or equal to negative 55 millivolts. So that might be another shocking feature for you, the fact that both of these types of ion channel have the same threshold potential. However, when you've learnt about the action potential, you've probably learnt that voltage-gated sodium channels open far before the voltage-gated potassium channels, and that is true. Even though they're both activated to open at the same electrical potential difference across the cell membrane, the same threshold potential, the kinetics of the opening of voltage-gated sodium channels is much quicker than the kinetics of the opening of the voltage-gated potassium channels. I mean that this arrow, this activation arrow, occurs much quicker for these ones than it does for these ones. It's very, very slow, the activation process for voltage-gated potassium channels. So they're not going to instantly open, whereas these ones are pretty much instantly going to open. There will be a delay before these open. So let me now draw the classical graph. So we'll put this here. So this is the classical graph to draw for an action potential. We are putting the electrical potential difference across the cell membrane on the y-axis, and on the horizontal axis, of course, we're going to have time. So we start off with the electrical potential difference across the cell membrane comfortably at negative 70 millivolts. Then, when we stimulate the neuron, so when we stimulate its dendrites, positive charged ions are going to come in, and they're going to depolarize the electrical potential difference across the cell membrane at the axon hillock. So now let's imagine it's been depolarized up to the threshold potential, which is here, and that's negative 55 millivolts. Then what's going to happen is both of these ion channels in that little region of cell membrane here in the axon hillock, and I think I will just draw a little box around here. So in purple here, this is the axon hillock. So the voltage-gated sodium channels and the voltage-gated potassium channels that are in this region, and there will be loads of them, they're all now going to be activated to open. But the voltage-gated sodium channels, they actually do open much, much quicker. So the voltage-gated sodium channels open whilst the voltage-gated potassium channels are still just thinking about opening. Therefore, what's going to happen, voltage-gated sodium channels in this region open, they're going to allow sodium ions to come into the cell. Remember the concentration gradients of sodium and potassium across the cell membrane. Sodium concentration extracellularly is around 145 millimolar, whereas the sodium concentration intracellularly is around 12 millimolar. Potassium concentration extracellularly is around 4 millimolar, whereas potassium concentration intracellularly is around 155 millimolar. So this is sodium and this is potassium. Also think about the electrical potential difference across the cell membrane. It's still negative 55 millivolts. It's lower inside the cell. Sodium ions want to be where the electrical potential is lower. Positively charged ions do not like being in high electrical potential areas. So they want to come into the cytoplasm of the cell. So you're going to get sodium ions moving into the cytoplasm of the cell, and I'll draw this on here. So sodium ions come in when you open the voltage-gated potassium channel, the voltage-gated sodium channels, and of course the voltage-gated potassium channels have not opened yet. So what's going to happen? The electrical potential difference across the cell membrane zooms upwards, the upstroke of the action potential, and it actually gets to positive levels, so it goes up to plus 30 millivolts. Now just a little explanation here. the electrical potential difference across the cell membrane is going to become positive, i.e. the electrical potential intracellularly is going to become higher than the electrical potential extracellularly. These are going to swap round. This one's now going to be higher than this one in this little region of cell membrane here that's undergoing the action potential. Now you might think, well, aren't the sodium ions going to stop coming in now, because now the electrical potential intracellularly is higher than extracellularly, and the positive charge of the sodium ions doesn't want to come into an area where the electrical potential is higher. And you're right, it will be a factor that slows down the current, but remember the massive concentration gradient. This is still going to overpower a positive electrical potential difference across the cell membrane when it's still only a small positive electrical potential difference across the cell membrane. Of course, if you made this large enough, it would overpower the concentration gradient and you wouldn't get sodium ions moving in anymore. But at these levels, that's not strong enough to overpower the concentration gradient, so you always get sodium ions still coming in. So why does it stop then at plus 30? It's because the voltage-gated sodium channels, they were only in the open state transiently, and that time is up. They move now into the inactivated state. They go into the closed inactivated state, and therefore no more sodium ions come in. So in that tiny little bit of time there, that's the time where the voltage-gated sodium channels in this region of cell membrane here have now closed. Now, just as the voltage-gated sodium channels have been through the entire process, they've been through activation and inactivation, and they're now in their stable state now that the electrical potential difference across the cell membrane is greater than or equal to the threshold potential. Now, the voltage-gated potassium channels have just about got ready to open. They've decided that, they've had enough time now and they're ready to actually open. So they're going to just go through the activation process at this point now. So you're going to get the voltage-gated potassium channels now opening. So they go into the open state transiently, and of course potassium ions can now move. And which direction are potassium ions going to move? Of course, they're going to move outwards, because the concentration is so much higher inside the cell than it is outside the cell. So the potassium ions are going to move from the inside of the cell to the outside of the cell. So you're now going to get positive charge moving out of the cell. That will lower the electrical potential intracellularly, raise the electrical potential extracellularly, so that will repolarize the electrical potential difference across the cell membrane. It will take it back down to being negative. Okay? You also have to factor in more than just the concentration gradient, of course. You have to factor in the fact that currently our electrical potential difference across the cell membrane is plus 30. These positive ions really do not want to be there, so both the concentration gradient and the electrical potential difference across the cell membrane are screaming for the potassium ions to want to leave. So indeed, that's what's going to happen. They're going to leave, and the electrical excuse me, and the electrical potential difference across the cell membrane is going to come crashing back downwards like so. So I need to explain a few things at this point. So it comes crashing back down, it goes into the negative levels, and again you might argue, well, now aren't the potassium ions going to want to come back in because of the negative electrical potential difference? And I would argue again, look at this massive concentration gradient, that still wins basically at all of these levels. You'd have to take it down to about negative 80 to 90, negative 85, let's go for in the middle, before the potassium ions would actually not want to leave anymore because of their concentration gradient. It will slow it down, the fact that the electrical potential difference is now telling them to come back in rather than get out, but it won't stop a net current of potassium ions still leaving. Okay, the other thing to talk about is, look, this continues on well below the threshold potential. We go down to actually around negative 75 usually. So usually this repolarization phase of the action potential gets us hyperpolarized. It takes us down to negative 75 millivolts. How is this working? So the voltage-gated potassium channels have gone into the open state, and they're in the open state, then we hit negative 55 millivolts. We cross back down into negative 55 millivolts. What happens now? They were going on their way to the closed inactivated state, but do they want to go to the closed inactivated state now? Because the electrical potential difference across the cell membrane is now below negative 55 millivolts. So now they say, hang on a second, let's go back into the closed resting state, and they start to deactivate rather than inactivate. Okay, so the voltage-gated potassium channels at this point are deactivating. So you might say, well, why doesn't this downstroke of the action potential stop then at negative 55 millivolts? It's because voltage-gated potassium channels cross this bridge extremely slowly. They took ages to activate, they also take ages to deactivate. So this is not a quick process, so they're still going to remain open for quite a while before they actually get round to deactivating and closing, and that's why you go down to negative 75 millivolts. Now, just to point out that some of the voltage-gated potassium channels will have actually made it into the inactivated state. Not all of them will have been faffing around in crossing this bridge. Some of them will have gone into the inactivated state. When we go back down to negative 55 millivolts, they'll have to then do both of them. They'll have to de-inactivate and deactivate. But a lot of them never actually get into the inactivated state. They just go straight back into the closed resting state once you cross back down below negative 55 millivolts. Okay, so at this point we've had all of the voltage-gated potassium channels return to the closed resting state. The voltage-gated sodium channels, once we've gone below negative 55 millivolts, they will now start to do the same. They will de-inactivate, temporarily go into the open state, but they'll be in the open state ridiculously transiently because, remember, they cross this bridge very quickly. They activate and deactivate very quickly, so they move instantly back into this one. So that's why they're not going to have much of an effect. Not much sodium is going to come through that transient open state. So voltage-gated sodium channels, this bridge is very, very quick. This movement is slower, but still reasonably quick. Whereas for voltage-gated potassium channels, remember, this one's slow and this one is slow as well, so they're both slow, and that is significant. It explains why they don't open until we're at this point, and why they don't close when we're at negative 55 millivolts. So, voltage-gated sodium channels and voltage-gated potassium channels are now both closed. What happens now? We're at negative 75 millivolts. Well, of course, we now just return to having the leaky sodium currents and the leaky potassium currents again, and the only electrical potential difference across the cell membrane where there is an equilibrium is negative 70 millivolts. So the Goldman-Hodgkin-Katz constant field equation gets its way, and of course, you will get currents, net currents moving across the cell membrane to return the electrical potential difference across the cell membrane to negative 70 millivolts. So remember, this is the only electrical potential difference across the cell membrane where the leaky sodium currents in match the leaky potassium currents out. Remember, at resting membrane potential, the way we maintain this is because we've got leaky sodium channels, leaky potassium channels, sodium is coming in, potassium is coming out, but they match one another provided that the electrical potential difference is this. And when the electrical potential difference is not this, when it's lower, that will of course reduce the potassium current going out, it will increase the sodium current coming in, so you will now not have them balanced, you'll have a net positive current inwards, which will then depolarize you back up until you've got the resting electrical potential difference across the cell membrane. And of course, the sodium-potassium pump is then there to pump sodium ions back out and potassium ions back in to maintain the ionic gradient. So that's what's going to happen at this point. The equilibrium, amazing physical chemistry is going to take hold. The constant field equation, the Goldman-Hodgkin-Katz constant field equation, will run this and return you back to negative 70 millivolts. Okay, right. So, there is our discussion of the action potential complete. Oh, no, we've got one more thing, very crucial thing to actually talk about with the action potential, and then we'll talk about the drugs and how they're going to work. Very crucial thing is, how does the action potential actually propagate? So the action potential has occurred at this little portion of cell membrane. So it's occurred here. We've had this transient reversal of the electrical potential difference across the cell membrane. How does this propagate to the next bit? Well, it's because when this is undergoing an action potential, in the upstroke of the action potential, you get lots of sodium ions coming into the cytoplasm here. They will diffuse to the cytoplasm underneath the neighboring portion of the membrane, and that will cause this initial depolarization that was caused by these ions in the case of the axon hillock. So that will cause this bit to then fire an action potential, and then it will propagate onto the next bit, and it will propagate along and on and on. So it's like dominoes falling. Once one little bit of cell membrane has undergone an action potential, its neighbour will undergo an action potential, and on it goes. And of course there is a very fancy, nice key term here for that process. It's called saltatory conduction, when the action potential conducts along by one portion of membrane undergoing an action potential, causing the neighbouring portion to undergo an action potential, causing the neighbouring portion to undergo an action potential. Saltatory conduction actually refers to anything that sends a signal by the domino effect, basically. Something here causes something in its neighbouring region, causes something in its neighbouring region, etc. Anything that sort of follows that basic conduction strategy is called saltatory conduction, and action potentials certainly follow this concept. Now, important to understand at this point is that if for some reason the amount of sodium coming in the action potential at this little bit of membrane was to be reduced, maybe by the fact that we had given a voltage-gated sodium channel blocker that blocked some of the ion channels, that would stop the action potential from being conducted on. If you're not getting enough sodium in, then you're not going to produce enough depolarization necessarily of the electrical potential difference across the cell membrane of your neighbouring portion of cell membrane, and then the action potential won't conduct on. And this is the way that use-dependent voltage-gated sodium channel blockers are going to succeed in blocking action potentials from firing. So, let me now tell you what these drugs are going to do. So, we're now going to introduce the use-dependent voltage-gated sodium channel blocker into the story. So we will do it as a little green blob here. Now, it's only going to, and I'll just label this up as drug, it's only going to interact with the voltage-gated sodium channels, nothing to do with the voltage-gated potassium channels. So here is the evil drug, topiramate or sodium valproate. In fact, no, it's the hero. Here's the heroic drug. What is it going to do? So it's going to block voltage-gated sodium channels. It binds to the pore of voltage-gated sodium channels and blocks ions from being able to move through. However, it only binds to voltage-gated sodium channels when they are actually in the open or closed inactivated state. This is why it is called a use-dependent voltage-gated sodium channel blocker, because it only actually blocks voltage-gated sodium channels when they are being used. If I had my neuron here and I bathed it in this drug and I never ever induced an action potential to fire in this neuron so that the electrical potential difference across the cell membrane was maintained at negative 70 millivolts, all of the voltage-gated sodium channels were in the closed resting state, the drug would not bind to a single one of those voltage-gated sodium channels because it cannot bind to them unless they are being used. It only binds to them in the open or the closed inactivated state. So, we need to use this neuron then, otherwise it's a very boring story. So, let's now activate our neuron. So, here comes in the positive charge, and we, of course, depolarize the electrical potential difference across the cell membrane of our axon hillock here. Okay, so what's now going to happen? The voltage-gated sodium channels are all going to open, and when they open, the drug that is now bathing the neuron, it can enter them. It can enter their ion channel here, and it can bind to them, like so, and it will block that ion channel. So it's a use-dependent voltage-gated sodium channel blocker. And you might say, well, why doesn't this just block action potentials full stop? Because now that's going to stop the sodium ions coming through. That's going to stop the entire thing. That's going to stop the upstroke. The answer is, it's not very fast to actually bind onto these voltage-gated sodium channels. So it's not actually too detrimental. You're getting over-dramatic as to how much effect this drug is going to have. Most of the voltage-gated sodium channels in this area will not actually be blocked by the drug whilst they are in the open state. So in this bit, some of them will actually get a drug binding to them, and therefore the upstroke will be reduced a little bit. So it might not get up to quite plus 30 millivolts now. It might get a little bit lower, so it might look like that now. I.e. the upstroke has been reduced, the depolarization has been reduced a little bit because some of the voltage-gated sodium channels were blocked in the process when they were actually open. However, when they now inactivate, when they go into the closed inactivated state, they are still in a state where the drug can bind to them. You can see the pore is nicely open, and the drug can still come in here and bind to them, and that's actually when a lot of them are going to get the drug binding to them. In this bit here, when they're in the closed inactivated state, because the drug actually loves them when they're in the inactivated state. It much prefers them in this state to being in the open state. It loves to bind to the inactivated state. So only a few of them will actually be bound to and blocked in the open state, so there's action potential upstroke isn't going to be too detrimentally affected. It will be affected a tiny bit, but not detrimentally. Whereas now, when we're in the inactivated state and the voltage-gated potassium channels are doing their bit of the action potential, now loads of our voltage-gated sodium channels, in fact, to make it simple, let's just say all of them are now going to get the drug binding to them, okay? And it's blocking their pore. Of course, their pore's not actually conducting anything because the inactivation gate is also blocking their pore. So you might think, well, what's the point of that? That's not going to do anything. Here's the clever bit then. So let's now follow the action potential on. So this comes down, we go back, the electrical potential difference across the cell membrane comes back down. That action potential will be conducted. I want you to be convinced of that because, look, the action potential here, in this axon hillock, I've said, okay, the upstroke might be affected a little bit, but overall, the action potential is fine. And this upstroke is still big enough to let in enough sodium ions that enough will diffuse to the neighbouring portion of the membrane to cause an action potential there. And when the action potential occurs in that neighbouring portion of the membrane, the exact same thing will happen. Yes, the upstroke will be a little bit smaller because the drug will be binding to some of the voltage-gated sodium channels in that region whilst they're in the open state and blocking them from letting in sodium that they otherwise would have. But to be honest, it's not having that big an effect on the upstroke. So that action potential will conduct absolutely fine. It only is blocked from conducting if the upstroke is too small. And at the moment, our voltage-gated sodium channel has not, our use-dependent voltage-gated sodium channel blocker has not detrimentally affected the upstroke, so everything is fine. So what I've convinced you hopefully there is that putting this drug on will not actually affect the action potential conducting along. Yes, it will mean the upstroke is slightly smaller, but that just doesn't matter. As long as it conducts along, that's the whole point of an action potential, remember. It's a propagating signal. As long as it gets to the axon terminal, it's done its job. That's the fundamental signal. It doesn't matter that the actual propagating electrical potential difference disturbance wasn't quite normal. As long as it propagates, the signal's carried. Okay, now let's think about what happens next. So, when you bring the electrical potential difference across the cell membrane back down to below negative 55 millivolts, what wants to happen now? Because at the moment, all of my voltage-gated sodium channels in this portion of membrane, and indeed it will be in all of the membrane, because it's all going to fire the action potential, but let's just talk about the axon hillock membrane. In this portion of the membrane, they'll all be in the closed inactivated state with the drug bound to them. Now, the drug is capable of stabilizing the inactivated state. So, when we go below negative 55 millivolts, of course, normally the closed inactivated voltage-gated sodium channel wants to then return to the closed resting state by going into the open state first, transiently. It wants to de-inactivate, and then it wants to deactivate. And remember, it de-inactivates slightly slowly. This takes time crossing this bridge. Crossing this bridge, the deactivation is extremely rapid. So it takes a little bit of time to de-inactivate, and then it will deactivate, and that time that it takes to deactivate is the same sort of amount of time that it took to inactivate, so this sort of time here. Okay, so normally, by the time we'd want to fire another action potential, they would all have gone back to the closed resting state and everything would be ready and we could do it. However, now this drug slows the whole process down. You see, to go back into the closed resting state, the drug has to come off. So now what has to happen? The drug has to come off, and then it will move in, and concurrently with the drug coming off, it will move into the open state transiently, and then go into the into a closed resting state by deactivating. So all of it becomes one effectively. It can't. When it wants to de-inactivate, when it wants to cross this bridge, it will also end up chucking the drug off at that same time, and then instantly, once it's de-inactivated, it will then deactivate. So view it all as one process, don't fragment it up. If it wants to go back into the closed resting state, it has to chuck the drug off. Okay, is the key thing here. And the drug doesn't want it to do that. The drug is kind of sitting there saying, no, don't do that. The channel, of course, wants to go back to this state because we're below the threshold potential, but the drug is saying, no, stay in this state. I can bind you in this state, whereas if you go into that state, I can't bind you. You're going to chuck me away. So it ends up taking much longer to return to the closed resting state, the normal. It stabilizes the inactivated state. So now, if you don't wait long enough before trying to fire another action potential, not all of your voltage-gated sodium channels in this portion of cell membrane will have actually returned to the closed resting state, and that's the crucial thing here. So firstly, let me explain what will happen if you do wait long enough. So let's say you wait a long time now here, and I don't mean a really long time, a few, milliseconds, or whatever the time period is. I don't know what the specific time period is, but it will be a reasonable amount of time. So if you wait a reasonable amount of time, what will before you try to fire your next action potential, what will have actually happened is all of the voltage-gated sodium channels will have got around to chucking the drug off, and they will be back in the closed resting state, and therefore everything's back to the way it was in the beginning. Everything's ready, set up, all for the action potential to fire again. So if you get stimulation to fire another action potential, what's now going to happen? The exact same thing as happened previously, okay? And what will happen is you will depolarize the electrical potential difference across the cell membrane up to negative 55. Our voltage-gated sodium channels in this region that are all currently in the closed resting state, they will go into the open state, and again the drug will come on, but not much of the drug will come on in the open state, so it will reduce down the action potential upstroke again, but that doesn't matter as long as it's not reduced it too much that it can no longer depolarize the electrical potential difference across the neighbouring portion of the membrane enough to induce an action potential in it. As long as it can still do that, then the signal conducts. And then the exact same thing happens, so the signal will conduct along, everything was fine. So what I've just shown you there is provided that you have a neuron that doesn't want to fire the next action potential too soon after the first action potential, this drug, these use-dependent voltage-gated sodium channel blockers, will not have any detrimental effect on its firing action potentials. Yes, it will mean that the upstroke of the action potential at any portion of cell membrane is slightly smaller, but that difference isn't big enough to stop the thing conducting. If you gave a drug that was enough to reduce the upstroke significantly enough to stop the action potential from firing, that would of course stop all neurons from firing action potentials, and therefore it would kill you. And that is not what these drugs do. We don't give them in the sort of doses where they would do that. We give them in a dose where they only reduce the action potential upstroke a little bit, and therefore they don't block the neuron from firing action potentials. And as long as you wait enough time, you'll be able to do the same thing all over again with no trouble at all, and your action potential firing will not be affected by these use-dependent voltage-gated sodium channel blockers. So this is wonderful. Now, let's look at the important bit. What happens if our neuron tries to fire an action potential too quickly? So if it gets impatient, if this neuron's behaving very weirdly, being far too overstimulated and wants to fire an action potential extremely quickly after the first action potential, what's going to happen this time? Well, the answer is that the voltage-gated sodium channels, they're not going to have all recovered. Let's say a great chunk of them haven't. Let's say 75% of them haven't actually gone back into the closed resting state yet. Let's say 25% of them have managed to do it. So 25% of them have gone into the closed resting state. The other 75% are still this picture here. They're in the closed inactivated state with the drug bound to them. Now, here comes the stimulation to fire another action potential. It will depolarize the electrical potential difference across the cell membrane up to negative 55 millivolts. What happens now? Well, the 75% of voltage-gated sodium channels that are still in this closed and activated state with the drug bound to them, they say, oh, bravo, look, the electrical potential difference across the cell membrane is now above negative 55 millivolts. We no longer want to go back into the closed resting state. We are perfectly stable like this, because this is the stable state to be in at above negative 55 millivolts. Bravo! So they're going to remain now in the closed inactivated state, and they're certainly not going to conduct any sodium ions in. The other 25% of voltage-gated sodium channels that were in the closed resting state, they will now do the normal thing. They'll go into the open state, they'll let in some sodium ions, and now some of them will then get the drug bound to them, then they'll go into the inactivated state, and all of them will end up with the drug bound to them, so that all of that 25% will end up again in the closed inactivated state with the drug bound to them. Now, the question is, what sort of an action potential upstroke will that 25% of voltage-gated sodium channels have produced? And the answer is in this sort of picture here. It will produce something that looks like this, won't it? It will produce a tiny little action potential upstroke because there is only 25% of them actually opening. And what's happened to all that 25% that had recovered? They're now all in the closed inactivated state. So 100% of your voltage-gated sodium channels are now back in the closed inactivated state with the drug bound to them. Now, this feeble little action potential that you've been capable of producing in this portion of cell membrane, is that going to have brought in enough sodium ions that it will spread to the neighbouring portion of the membrane? The answer is no. And now you see the action potential has been blocked. So this action potential that it tried to fire too frequently or too quickly after the first one has been blocked. Now, let's think about what would happen if it now tried to fire a third action potential too quickly after this pathetic second one that didn't even work in the first place. Okay, didn't actually conduct along the axon, so no signal occurred, no signal was sent. Well, again, what will happen? If it tries to fire it again too frequently, what will have happened? Not all of our voltage-gated sodium channels will have returned to the closed resting state. Remember, after the second one again, all of them were now in the closed inactivated state with the drug bound to them. So we're back in the position we were after the first action potential. So now if you give them only the same amount of time again, only 25% of them will get back into the closed resting state, and then you'll be trying to fire an action potential with only 25% of your voltage-gated sodium channels, and it won't work again. So, and if you keep trying to fire action potentials too frequently, none of them will actually work. You won't get any of them firing along, and you will just reinstate the block. The ones that have recovered, you're just blocking them up again by making them open. You make them susceptible to the drug. You return them back into this useless state where they've got the drug bound to them. So you just reinforce the block every time you try and stimulate the axon hillock to fire an action potential now, but you don't actually succeed in generating an action potential that's big enough to propagate along the axon. And this is the way that these incredible drugs will block all action potentials firing in a neuron that is trying to fire action potentials too frequently, whereas they will not cause a problem in neurons that are trying to fire action potentials at a normal frequency, because if you leave enough time, all of these voltage-gated sodium channels with the drug bound to them will return back into the closed resting state eventually. They do want to return into that state, it's just that the drug holds them up hugely. And as long as they've all returned back into the closed resting state, then you will have a big enough action potential generated that it can propagate along. Okay, so there is that incredible mechanism. It is a very, very important mechanism to understand. This is the way that a huge number of the anti-epileptic drugs work, and of course this is how topiramate and sodium valproate work. So overall, these drugs have succeeded in blocking all action potentials from firing along neurons that are trying to fire too frequently, and this may underlie its effect in migraine. It may mean that it blocks the susceptibility to cortical spreading depression. Okay, and with that, we finish our discussion of migraine headaches. In the next video, we will move on to our third type of primary headache, which is cluster headaches.